Hello, my name is Anke Hagen. I'm a professor at the Technical University. Today I would like to introduce you to the classical ammonia synthesis. I will start with talking about ammonia, a very general information about some aspects of ammonia, then go to the ammonia synthesis as such, and then into more detail of the Haber-Bosch process. Ammonia, a few of the general properties. Ammonia is a very simple molecule, NH3. It's a colorless gas with a very characteristic smell. It's toxic. It is easy to liquefy. Already at 8 bar and 20 degrees centigrade, you can store it as a liquid ammonia. And maybe this is one of the aspects that has made it more interesting in the recent times to use it potentially as a fuel, because in addition of very attractive storage properties, also the energy density here in energy content or heat of combustion is comparable per mass to methanol, a bit lower than gasoline, and it's also very advantageous in terms per volume, not only per mass, so if you want to fill it into a tank. That ammonia could be used as a fuel is actually not a new idea. Already at the beginning or in the middle of the last century, there were attempts to fuel trucks and buses with ammonia, and it was realized actually different places in Norway and in Belgium. And there were a number of vehicles running successfully on ammonia. However, as we all know, that was not a really commercial breakthrough, as later on we see that these trucks and buses rather run on diesel or gasoline. There's another aspect, ammonia. I'm showing here the ammonia production worldwide, which starts in the middle of the last century and then it accelerates. There's a sharp increase of the production volume of ammonia. And that is actually quite a significant contributor to global emissions, to CO2 emissions connected to the synthesis of ammonia, and it consumes also a significant amount of energy. Why is that the case? So why are we using so much ammonia? And that relates on the use of ammonia as a fertilizer. When we are looking, the blue line is how the world population has developed. It stops here at 2015. Now we know we have even exceeded significantly the 7 billion, having 8 billion for the moment. And the red line shows how much we would be without ammonia-based fertilizers. So you can see that almost half of the world's population depend on synthetic fertilizer based on ammonia, and that also explains the high increase of the production volume. And when we are looking in total how ammonia is used, then most of the ammonia nowadays go to the fertilizer industry, a few to other sectors, textile, explosives, and that is a bit more specified in this ammonia tree, where you see that you are starting from ammonia, going through different intermediate products, nitric acid, urea, and then you end up in a large range of products, not only fertilizers, also dyes, deposition layers, protecting layers, of course, fertilizers, pharmaceuticals, and so forth. So ammonia is a large-scale chemical nowadays. And that brings me to how can we synthesize, or how do we synthesize ammonia? The reaction, or how can we obtain ammonia, is very simple. You react nitrogen with hydrogen to give ammonia. It's an exothermal reaction. That means if you go to lower temperatures, you would get more ammonia yield. And then when you count the molecules, we start with 4 molecules, end up with 2 molecules. That means if we increase the pressure, we would also shift the equilibrium towards the ammonia side. However, if we would mix nitrogen and hydrogen, actually nothing would happen. The activation barrier for this reaction to happen is very big. In fact, that we only can reach this reaction to happening by using a catalyst. The next figure shows you just as an illustration how temperature and pressure affect the yield of ammonia. So the higher this curve, the more ammonia we are getting. And you see here the lines 1, 2, 5 up to 50 bar, high pressure. So the higher the pressure, the more ammonia we are getting. And here this is the temperature axis. The lower we go in temperature, 650 Kelvin is here, and at 600 Kelvin, also the more ammonia we are getting. And these lines are just an insert that shows you the curve at 1 bar atmospheric pressure, or just enlargement at the lower temperature, and only for 1, 2, and 5 bars. So the reaction wants lower temperature, higher pressure, and a catalyst. Now that leads me to the catalyst. I have plotted here a few elements of the periodic table. And here I'm showing some interaction strength with nitrogen that nitrogen has with the different elements. As you know, nitrogen is very inert. Nitrogen is in the air and not really very reactive. So if we are using elements on the left-hand side, they interact very strongly with nitrogen. Actually, they form a chemical bond, a nitride. That is, of course, not very suitable for a catalytic process where I just want to kind of activate nitrogen and not want to have a nitride as a product, like a metal nitride. When I then go to the other group of elements here on the right-hand side, they have quite a very weak interaction with nitrogen. So there, it is not sufficient to bring it into the right shape to receive hydrogen to form ammonia. However, when we go into the middle range, iron, ruthenium, osmium, there we actually have quite the right interaction strength that nitrogen is interacting with these elements and is able to then react with the hydrogen to form ammonia. And this is just a very qualitative expression of this interaction strength that has this top in the middle where you have quite the right interaction that is needed to activate nitrogen for the reaction with hydrogen. So if we go to the left, we have 2 strong interaction, and to the right, we have 2 weakened interaction. If we look at the reaction nitrogen plus hydrogen give ammonia, it looks very simple. Just 2 molecules are reacting and giving another molecule. However, in detail, there are many elementary steps that are proceeding or that have to develop in the right speed and to the, let's say, and to the right extent. For example, we are starting from nitrogen from the gas phase. We need an adsorption site, which is a star, and then we have adsorbed nitrogen molecule. That together then with another adsorption site splits into 2 nitrogen atoms. And these are the key. They react with adsorbed hydrogen to form a first hydridation step, so to speak, NH, that then react further with more hydrogen adsorbed species to the final ammonia, NH3, and ammonia adsorbed has to be desorbed into the gas phase. And this is, of course, one of the first steps as well. That is the dissociative adsorption of hydrogen. So you get hydrogen atoms adsorbed that then can react with the adsorbed nitrogen. So there's a huge range of reactions going on, adsorption, desorption reactions. And the rate determining step, that means the slowest step, is actually the dissociation of the nitrogen molecule to 2N. So this is the step that determines the overall reaction rate. We can also express this as a kind of energy at the energy scale. So here you have the energy, and here you have the single steps that I just showed you. And we're starting from from nitrogen and hydrogen, and then we are ending up with ammonia, which has a slightly lower energy. If we would rely on gas phase, we would step here up very high activation energies. So now here we are starting with adsorbing nitrogen, and then the reaction with adsorbed hydrogen atoms and so forth, hydriding nitrogen more and more to end up at NH3. And you see here that we have small activation barriers and then fairly stable intermediates requiring new activation energy until we end with the ammonia. And that is all for iron. If we would use other catalysts, then this picture would look quite different. This is the overall ammonia synthesis. So you know now we need lower temperatures, higher pressures, we need a very specific catalyst. And there is this, thanks to chemists, we actually now arrive at an industrial scale process called Haber-Bosch, because it was developed by Fritz Haber and Carl Bosch, 2 chemists. that developed this industrial scale ammonia synthesis. And that gave them the Nobel Prize, each of them in different years, and even not too far away, there was another Nobel Prize also connected to the ammonia synthesis by identifying some of the key elementary steps received by Ertel from Germany as well. The catalyst, we saw the interaction strength where iron was in the middle, giving almost kind of optimum interaction strength between the nitrogen and the catalyst or the element. And that is also the basis of the ammonia catalyst and the Haber-Bosch process, together with a promoter and then supported on some oxides. The apparatus which was used to before scaling up the process to industrial scale is shown here. So it's really in the earliest 1900s that this was developed and done and then scaled up by Carl Bosch, who was employed at BASF company. When we look at the Haber-Bosch process, it's very complex. It's in fact a combination of many different processes. On the left-hand side, this is actually has nothing to do with ammonia. This is only to receive the synthesis gas mixture we need for the ammonia synthesis, meaning here we are getting hydrogen and nitrogen that we are then using in the Haber-Bosch process here on the right-hand side. However, both processes are tightly integrated, which gives a higher system efficiency and makes the whole process cheaper. Let's first focus on getting hydrogen and nitrogen. Nitrogen, okay, it's a bit fairly easy, comes from the air at this stage. So nitrogen, oxygen comes in here. However, the hydrogen, where do we get the hydrogen from? In the classical Haber-Bosch, the hydrogen comes from fossil sources, from natural gas, methane. We are carrying out a steam reforming. That means we are mixing methane with steam on a catalyst, which gives us carbon monoxide and hydrogen. This is a kind of the first part, a reforming process. And then we have a second reforming where we now add air. So we have oxygen. Here it is steam we are adding. Here we are adding oxygen. So we are undergoing a partial oxidation. And that gives us a bit more carbon monoxide and more hydrogen. Now we have actually hydrogen and we have nitrogen. So we have already two ingredients. However, they are still mixed with carbon monoxide. And that we have to get rid of by, in a catalyst reactor, reacting carbon monoxide to carbon dioxide. So then, we are removing the carbon dioxide by a scrubber process here. So this is quite a huge processing to arrive at the synthesis gas. There's also pressurizing steps here involved, because later on the ammonia synthesis will also arrive or be carried out at higher pressure. Here in the scrubber unit, we are washing kind of away the CO2. And now we have finally the nitrogen-hydrogen synthesis gas mixture we want to use in the Haber-Bosch and in the direct ammonia synthesis. And that goes to the ammonia synthesis reactor. The temperatures are 450 degrees centigrade and 300 bar, so we really talk about high pressure here. Ammonia is produced, and the product stream that contains non-reacted molecules like nitrogen, hydrogen, and ammonia goes through a heat exchanger where we are utilizing the heat of this hot-off gas. And then we need to separate out the ammonia, and the non-reacted synthesis gas, nitrogen, hydrogen, goes back into the process. So we are recirculating the nitrogen and hydrogen. So this is the overall concept of a typical Haber-Bosch process in very simple terms. This reactor doesn't show too much. I have just one issue here. We say that it's an exothermic reaction and we would like to keep the temperature low. When you are forming ammonia, of course, it's getting hotter and hotter. And to avoid that the temperature is getting too hot, which would diminish the ammonia concentration, we are working actually with a multi-stage reactor that can have different designs. This is one example. So this is the whole reactor that is separated in different stages, and in between you would do the cooling in order not to overheat and in order to be able to extract most ammonia as possible. So coming back, this is a very complex picture, and that is also how it looks like in reality. So when you look into an ammonia plant, which is a picture showing here, it's almost a small city, because all the streams, gases and heat, media are interconnected with each other, tightly integrated to make use of the, let's say, off products from one process and using it in other. So this gives a very integrated system with the highest possible output. To summarize this classical ammonia synthesis, ammonia is very well known because we have made it for decades to make it into synthetic fertilizer that now feeds half of the world's population. We need a tailored catalyst for ammonia synthesis that has been developed in the early 1900s, which we are still using these days. And the industrial production relies on this catalyst and the process that was developed by Haber and Bosch with these iron-based catalysts working with at high pressure and temperatures around 450 degrees centigrade. With this, I would like to finish my classical ammonia synthesis presentation. Thank you for your attention.